Hi everyone. So we're coming in today, hopefully with a decent review of all of our transformations to our trig curves from last time. And so what I have up on the screen today is just a quick review of that in case there was any sort of struggle. But also what we're going to do then is we're going to kind of take dealing with our sine and our cos curves, and we're going to go to maybe next level of comfort. And what we're going to address today is actually sketching our sine and our cos curve. We're also going to add in at the very end us dealing with graphing a tan curve. So that's going to be maybe a little bit of a step back in terms of our process, but because it's our tan curve, I think that that's probably getting us quite far enough. So first thing I want you to do is just take a look at the screen that you have in front of you. And what you'll notice in blue is there are all the transformations given the function listed up above. So where you see as ugly of a function as what you could get, our a, our k, our c, our d, those are all the effects of those. You'll also notice in green that if the a was a negative value, then you would have a reflection. We should be good with all of those. It should go without saying, but I don't want to make any assumptions though, that we don't have to be concerned about a k value being negative because it's a periodic function. That is, your sine and your cos graph will repeat over and over again. And so the idea then of reflecting it in your y-axis is never needed. Now, there are some other things that aren't really needed either. However, we may get to a point, though, where we just say, if we need a curve to look a certain way, we can get there through different transformations than a reflection in the y-axis. So we never have to worry about our k value being negative. That hopefully is a review from grade 11. And what I want to add in on the right side is a little bit of review from grade 11 and just making sure that we're good with some language and some notation. So we should be good that the absolute value of your a value, so who cares about the sign of it, positive or negative, whatever number the a value is your amplitude. We have our best friend from last time in period equals 2 pi divided by k. We have to remember that in terminology, when we talk about a horizontal shift, the way we refer to that using trig curves is a phase shift. And lastly, our d. Because our d value is a vertical shift, and because the middle of every sine or cos graph is 0 horizontally, then whatever we shift it vertically, we're shifting the middle of the curve. And so y equals whatever that d value is the equation of the horizontal line that runs down the middle of your graph. That's referred to officially as the equation of the sinusoidal axis, but we often just refer to it as the equation of the axis. So there is a review of everything you had coming out of grade 11. What I want to do is I want to jump into the process of sketching today. And in order to do that, we're going to kind of take a step back for a second. And so what you see in problem 1 is just an activity I want you to go through very quickly. On the left side of those, or the left set of axes, go through, sketch the first positive cycle of your sine curve. On the right side, sketch the first positive cycle of your cos curve. Go now. You should be out in front of me. You should be able to beat me through this process. I am catching up to you. My sine curve starts in the middle and rises, falls, and comes back. My cos curve starts at the top and falls, rises, and comes back. I really don't like that little hiccup in the middle. That's going to drive me nuts. So I'm just making a little bit of an adjustment there. And I don't know if I made that any better, but there we go. Now, let's take a look at the instructions below. I want you to label the approximate y-intercept. If you can label exact, you always label exact. And at least one maximum point and one minimum point on each sketch. So, just a little note. Ensure that you have 3 points labeled on each graph. So, if we take a look at the first one, we know that this maximum would occur at pi by 2 and 1. We know that this minimum would occur at 3 pi by 2 and negative 1. I have a max, I have a min, I don't have my y-intercept. My y-intercept is 0. There you go. I have 3 points labeled, and I have those specific 3 points. On my cos graph, I have my y-intercept labeled, and this minimum occurs at pi negative 1. Now notice, we may think for a second that this y-intercept is also a max, and so I kind of get a 2-for-1 deal. Be careful. We have to make sure that 3 points are labeled. And so therefore, I would have to label this second maximum then at my 2 pi 1 to ensure that I have 3 points labeled. There we go. Now, you might be asking yourself, why did we bother doing this? Because what you actually just produced was a pretty formal sketch of your sine and your cos graph. I might argue we actually might have done a formal sketch for the first time. That as we progress to uglier functions, functions with a lot more changes to them, we need to ensure that we have those same things done. Okay, first off, it was the first positive cycle. So notice, on both my red and blue graph, I only have one cycle. No more, no less. What I mean by that is my red curve doesn't keep going up here going, yeah, but I've got some space. No. That once I get back to that x-axis, my first positive rotation is done. You'll notice that you have one max and one min labeled and the y-intercept. If a max or a min happens to be the y-intercept, then we have to make sure that we have one other one labeled. If we have all that done, you've got some formal sketches. So now what we're going to do is we're going to jump in and we're going to start dealing with some uglier graphs. As we deal with those uglier graphs, there's maybe 2 different approaches that we can use, and I want to kind of walk through them a little bit. There are benefits, positives, negatives to both approaches, but some may prefer one or the other. So the first thing that maybe we want to kind of focus in on might be the idea of starting with the equation of the axis. Now, if we know that the equation of the axis is the middle of my graph, then that can be a nice starting point for us to produce a sketch. So we're going to tackle a sketch dealing with that blue strategy first, starting with the equation of the axis. The other strategy we can get into can be focusing about your max or your min and dealing specifically with your max and your min based on horizontal and vertical transformations. And so these represent 2 different approaches for us to be able to go through and sketch a trig curve. I think they're both very useful, and quite often with you, I tend to use the blending of 2. But I think that if we're good with those 2 approaches, then we'll have little difficulty sketching our curves. So let's jump in and start playing around with some uglier curves. Okay, so take a look at the equation I've given you, and you'll notice that there's a lot more to that than just your basic sine curve. We're going to go through, we're going to label the approximate y-intercept and at least one max, one min point. We know that to sketch, we're going to do the first positive rotation, and we're going to ensure that that last part, ensuring that 3 points are labeled on each sketch, is satisfied. And it's those specific 3 points. Okay, let's jump into maybe an approach that we can take on the first one. And so previously I had mentioned about starting with the equation of the axis. And so when we take a look at that function that was given, we notice that that whole function is at the end shifted down 4 units. So I know then that the equation of my axis is at y equals -4. And for me then to be able to go through and deal with a couple key features is I can take that middle of my curve and now tie it together with my amplitude. I know that my amplitude is always half the height. So when I see that that curve has been vertically stretched by a factor of 3, then I know from the middle of the graph I have to go up 3 and down 3 to get to its extremes. And so right off the bat then, I know something about my maximum and my minimum points. I know the y value. The middle of my graph is at -4. So I know that the max has to be 3 above it at -1. My middle is -4. My minimum has to be 3 below it, -7. Some people, a lot of people, like starting with the equation of the axis, and then we tie in amplitude to find what is the maximum and minimum values of my graph. Okay, to work through that process, it gets us part way. And this is where I said about blending the two. That if I'm going to need my maximum and my minimum values, then I need to know the x-coordinates of each of those as well. And this is where transformations come in. So, the only things that is going to affect my maximum minimum locations in this graph would be anything that affects it horizontally. I've already dealt with the y-coordinate, so I know how it's been stretched vertically. I need to know what's going on horizontally, and that's where the 2 comes in. I know that that 2 means a horizontal stretch by a factor of 1/2. So that means whatever my maximum, my minimum occurred, wherever that occurred, they now have to occur half the distance to my y-axis. So I know that my normal max on my sine curve occurs at pi/2. So half the distance to that then would be at pi/4. I know that my normal minimum on my sine curve exists at 3 pi/2. So now I have to stretch that horizontally by a factor of 1/2, which gets me to 3 pi/4. If I were to go through and sketch a curve, finding the max and the min, requiring those to be labeled, that's the way I deal with it. Now, I do have some things that can be a check. And this is where I also said the blending of the two can help. You could go through and do everything vertical in one go. Take your normal sine curve. That fluctuates between 1 and -1. Vertically stretch it by a factor of 3, makes you go 3 to -3. You now shift that down 4. Does that match up with my maximum minimum values? Yep. Then I feel pretty good. So as we take a look at that process, then you have the means to check. You also have the means to check the x values of your max and your min. By finding the max and the min, I actually find my two extreme values, and I should be good that the distance between my max and my min horizontally should be half my period. For me to go from the top of my graph to the bottom of my graph, I've only gone halfway. To complete the full period, I would have to continue getting back to the max, hence the half the period. So if I was to take 3 pi by 4 and subtract my pi by 4, then I get 2 pi by 4, which is a pi by 2. That represents half my period. And so if I do a quick check and I say, well, I know that the period is 2 pi over k, and so I take that 2 and I sub it in, my period of my graph is pi. Is half the period pi by 2? Yep. Then I feel very confident about everything I've found. So I'm just going to get rid of those last 2 bits that we wrote down. Those were my checks. I never need to do that work, but they definitely increase the confidence level. The only thing that I haven't encountered now is I have to go through and I have to get my y-intercept. And so I know to find any y-intercepts, I can sub in x equals 0. Sine 0 is 0. And I get down to that. Oh, yikes. Silly mistake. 3 times 0 is 0. And I get down to that. Now, you'll also get a little confirmation that any of those transformations aren't really going to affect my y-intercept, at least not horizontally. So my normal y-intercept on my sine curve is 0. Vertically stretching that by a factor of 3 causes no change. Horizontally stretching it by a factor of a half causes no change. The only thing that's going to affect it is that minus 4, shift it down 4, there we go. So we get to that point where we found all that information off on the side. Now's our job to put it all together. Okay, we take a look at our points. I need to put on a y-intercept at negative 4. So say I call that negative 4. Now I'm going to focus up on my maximum, because if you look at the x-coordinates of your maximum and your minimum, I see that my x-coordinate comes first at pi by 4. That coordinate is going to get me to pi by 4 and negative 1. So when I draw my graph increasing to its max, I have to try to get to what I think would be a y value of negative 1. If I do, then I have to try to come down the same distance, and I finish at my first positive cycle. There is no need to label this point. In fact, don't. I have that as a picture. Now I can go through and I can label my points. I found that my max occurred at pi by 4, negative 1. My minimum occurred at 3 pi by 4, negative 7. And there we go. I'm going to put one line on just so we can try to see if we can get really, really good at this. I'm going to put on the equation of the axis. Now, I want to be really clear here. Don't ever include that into your solution. You'll notice that by me putting a dotted line down there, it actually makes it look like an asymptote. And it is not an asymptote. But by doing that, it gives me something to check. Does my curve look like it goes approximately the same distance down as what it does up? I also get a chance to then check, is the first half equidistant to the second half? And you'll notice that the second half of my red curve, I went a little too far down and it took me a little too long to get back. If I was a real perfectionist, I'd be saying, okay, I got to try to make each half of that cycle symmetrical. But overall, I'd be pretty happy with that picture. So to get rid of all that yellow and purple, if you were to just give me that red curve, perfect. Okay, let's keep working our way through, and we'll see a couple things that can arise that we've got to keep our eyes open for. So, as we take a look at problem B, we've got to ask ourselves, why are we covering B? And this one kind of comes in two parts. The first thing that I'd want you to address, and this is a big one, and I'd like you to put a star above it, is that negative. That this can be a bit of a trap problem for us because of what that negative does. And so I'm going to go through in a sec kind of an approach that might bring to light the way that negative could cause us a problem. Secondly, we haven't dealt with one that it deals with a phase shift, so the phase shift is also something that we're going to want to focus in on. So let's start off the problem the same way. But what I'm going to do is I'm going to kind of go opposite direction. So when I said I was going to kind of show two different routes through, I'd like to show you the second route this time. You're going to notice you're going to see some similarities with the first. But hopefully this can give you an alternate approach to creating a sketch. So the first thing is maybe I focus instead on coming up with my maximum and my minimums right now. Okay, I know that on my normal coast curve, my maximum occurs at 0 and 2 pi, and my minimum occurs at pi. So what I could do then is I could go on the hunt for those max or min values. So I go back to my base coast graph. My max is 1. Reflecting it in the x-axis is not going to affect that. Shifting it horizontally is not going to affect that. Horizontally stretching it is not going to affect. The only thing that's going to affect the max or min value is the +1. So my normal coast curve has a max at 1. This coast curve is going to have a max at 2 because of the vertical shift. You take a look at your coast curve, it normally has a minimum of -1. I shift it up 1, gets me to a minimum of 0. Okay, hopefully pretty smooth. Now we're going to get into the trap a little bit, and I'm just going to get rid of everything on there in a second. Okay, now I start to think about my max. So I think about my coast graph, and I know that my coast graph starts at the top and falls. Well, as soon as I see that I have a phase shift that's going to be left, then I know that this maximum is going to be moved off my first positive cycle. That means I can't use the first max to generate a labeled point. So I have to go to that next max, and that next maximum is going to occur down here at 2 pi. So I know then that my maximum occurs at 2 pi, and so what I'm going to do for that max is take 2 pi and then do my transformations to it. Okay, so the first thing is I notice that I'm going to reflect it, I'm going to do my transformations horizontally to affect it. So the first thing I need to deal with is I'm going to do a horizontal stretch by a factor of 3. So I'm going to take that 2 pi and I'm going to divide it by 3. Now what I need to do is I need to deal with my phase shift. And so now I need to shift that curve, I need to shift that curve to the left pi by 6. And that's why you see me subtract the pi by 6. Okay, I can just put all that together and do a little calculating. So I have a 2/3 minus a 1/6. I'm going to get a common denominator of 6. That would be a 4/6 minus my 1/6. So that would be a 3 pi by 6 or a pi by 2. And so I know that my maximum occurs at pi by 2. And maybe you can see that I just fell into my trap. That is by far the most common mistake that you're going to make if you use this approach. Maybe you can see it. I want to go back, and what I want to do is I want to highlight something that I asked you to highlight in the equation originally. That being that negative out in front. you may have noticed that I didn't take into account the reflection in the x-axis. So the focus then becomes, be careful that the reflection in the x-axis isn't the issue between the max and the min. It's not like I calculated my value wrong. What it is that because of the reflection in the x-axis, my maximum and my minimum changed. So what I'm going to do is I'm going to put on my base cos graph again, and all I'm going to do is reflect. And so what you'll notice is, as soon as I reflect that curve in the x-axis, what used to be a maximum now became a minimum. And so it's not like I wasted my time coming through and finding that value. What it is that I didn't really find the maximum value. I actually found the location of my minimum. Sorry, that jumped on the screen there. That when I found that pi by 2, I actually found the x-coordinate of my min. You'll notice that the reflection in the x-axis makes that a bottom on my curve. Now when I do my horizontal stretch by a factor of 1/3, that's what brings me into 2 pi by 3. And then when I shift it to the left pi by 6, that's what brings me in at a value of pi by 2. So, key thing for us to remember, and if I had to give you a suggestion, the first thing I always look for, always, as I'm going through and I'm transforming a graph, is I look to see whether that graph has been reflected. Because that's going to alter what I'm thinking of when I start to look for my max or my min. And so, I really didn't find a max there. What I was really finding was my minimum. Okay, so let's walk through this like we're really focused now and we know what we're doing. We've worked through this enough times, we're not going to make that mistake. So I need to find my max. Well, that means since that curve is reflected in the x-axis, I'm actually looking for the location of a minimum. Because as soon as I reflect it, minimums become maximums. So where does the minimum occur on my normal cos curve? It occurs at pi. And now I'm going to take that value of pi and I'm going to do all the transformations to it. Horizontally stretch it by a factor of 1/3, so multiply it by 1/3 or divide by 3. Now shift it to the left, pi by 6. So if I was to simplify that, then I have a 2/3 minus my 1/3, 2/6 minus my 1/6, and therefore I get down to a pi by 6. Okay, the only thing left to find is the easiest thing to find. We're going to go through and we're going to find our y-intercept. So I know to find any y-intercept, my x value is 0. And this is one that I can actually calculate because I know the value of cos pi by 2. The value of cos pi by 2 is 0. And so I come in then on a y-intercept of -1. Sorry. I come in on a y-intercept of 1. So let's put all those properties together. Okay, first off, my y-intercept puts me at 1. I take a look. Pi by 6 is my max. Pi by 2 is my min. My max is going to occur before my min because pi by 6 comes before pi by 2. And so I can go through and I can plot those values. So I'm going to go through and now sketch my curve up to its max, down to its min, and back. One positive rotation. Let's label everything we've got. I have my max occurring at pi by 6 and 2, and I have my minimum occurring at pi by 2 and 0. So what do I want you to get out of that one? Be focused on the reflection. The fact that negatives, when reflected in the x-axis, change maxes and mins. Secondly, we always have our last method that we sketched to be able to go through and use as a check. I can check that the middle of my graph is at 1, and my amplitude is 1, so that means from my middle that I have to go up 1 or down 1 to get to the max or the min. That checks out. I'm feeling confident. I also know as I go through that when I examine my stretches, that I'm going to have the difference between my max and my min be half my period. And so if I was to calculate pi by 2 minus, well then if I got a common denominator of 6, I would be 3 minus one of them. So I'm 2/6 or a pi by 3. That's half my period. And so if I do a quick check and I was to calculate using my best friend that my period is equal to 2 pi divided by k, then it's 2 pi divided by 3. Yep, 1/3 is half of 2/3. I feel really confident in my sketch. Okay, I really don't think we've added in, missed anything that's major as we go. What I want to do is I want to throw in what could be pretty close to like the ugliest one you could deal with. Okay, so let's take a look, and you look at that equation, and that looks pretty ugly. Apart from a reflection in the x-axis, it's got everything else that we need. So what I want everybody to do is pause the video now, give it a shot, and we'll see if we match up in the end. Okay, we're back. So again, I'm going to go through and use a blended kind of form for us to be able to sketch, and then we'll see if we match up with a little bit of confirmation. So the first thing I might focus in on is my equation of my axis. I know that the middle of my graph has to be at y equals 4, and I know that the amplitude is 1/2, which means I have to go up a half, down a half to get to my max or my min. So I'm going to focus in then that my max and my min, I already know their values. My maximum is 4 plus a half. I don't care if you want to write 4.5 because it's exact. Or if you wanted to go through and say that we've got that as fractions, that I am 9/2. Minimum is going to have to be the middle 4 down a half, so we're going to get to 7/2. Okay, now what I need is I need the x-coordinate of both my max and my min. So I focus in, there was no reflection, so wherever my max normally is, that's the same case. So I'm going to focus in then on finding my max of my sine curve, and I know that my max normally occurs at pi by 2. So now what I need to do is I need to do some transformations. So the first thing I'm going to focus in on is that 1/3. I know that a 1/3 sitting there means that I have a horizontal stretch by a factor of 3. I know I have to take the reciprocal. So that means that I need to multiply that pi by 2 value by 3. Then what I have is I have a shift to the right pi by 2. So I need to add to that a pi by 2. Okay, when I go ahead and I calculate that then, or simplify that down, then that means I'm going to have a 3 pi by 2 plus another pi by 2. So that's going to give me a 4 pi by 2. That's going to give me 2 pi. So I know that the position of my max has an x-coordinate of 2 pi. Okay, I'm going to do the same thing, and I'm going to deal with my minimum. Well, my minimum on my sine curve normally takes place at 3 pi by 2. And now I'm going to do all those same transformations to it. Horizontally stretch it by a factor of 3, then shift it to the right pi by 2. Okay, I simplify everything down now. So that's going to give me a 9 pi by 2 plus another pi by 2. So that's going to give me a 10 pi by 2 or 5 pi. There's the position of my min. Okay, last thing that we need our approximate value for our y-intercept. So I'm going to go through then. I know that my y-intercept occurs where x equals 0. And now all I have to do is simplify and then calculate. So I'm calculating the sine of negative pi by 6. That is a special value for me, so I don't even need a calculator for that. Now, if it wasn't a special value, then yes, you'd need a calculator to go through and push some buttons and get a decimal approximate. Hopefully, though, if we know we rotate back negative pi by 6, then that means I'm rotating into the 4th quadrant, so my sine is going to be negative. Pi by 6 is a small angle, which means I have a small opposite side. And so I can calculate that then and get a negative a quarter plus a 4, and that would be a 16, 15 quarters. Okay, now we got to put it all to create a picture. So if we were a little unsure, and I've caught up to you now, pause the video right now and see if you can take the information we've found and produce a good sketch. Pause it. Okay, or we're back and we found that information and now we're just confirming our curve. So I know that I have a y-intercept at a little less than 4. Now, the big part is I know that 4 is the middle of my curve. So I found that I was 4 minus a quarter. So when I begin to sketch my curve, I'm actually curving up a little bit, then down. What that means is, all the way back over at the end of my curve, I don't actually get back up to the middle. I don't get back to 4. That I should actually be a little less than 4. And there we go. Okay, the position of my max. I knew that I was going up first because my maximum occurred first. It occurs at a value of 2 pi, 9 halves. And my min occurs at a value of 5 pi, 7 halves. Now, I'm going to bet and say for most of us, we have a curve that matches what you see on the screen. And if this was an evaluation, I would give you perfect for that sketch. However, I do want us to just kind of take a look at it and just notice that that sketch is really skewed. Like, take a look at what your amplitude is. It's a half. That means your height is 1 unit. So the distance from this max to this min is 1 unit. But then when you take a look at the y value of your minimum, you notice that that's 7 halves, or 3.5. So this distance is 3.5. So if we want to really get good at sketching, we also have to kind of have in mind, what is the general shape of the graph? And so when we deal with a vertical stretch by a factor of a half, we notice that that makes the graph flatter. And then a horizontal stretch by a factor of 3 makes the graph flatter. That really what we have, or should have, is something that floats, more like what you see on that yellow graph. As I said, though, if you've got the red, I think you're doing great. Okay, there is it for us in sketching sine and cos curves. Those will be the only two graphs that you will be responsible for having to sketch. What we've left out, though, today is dealing with graphing a tan curve. And so what you see on the page now is the equation for your tan function, but you'll also notice that we've brought back our grid. What you're responsible for in our course is for going through and being able to graph a tan function. Not sketch it, graph it, which means that we are really going back to dealing with transformations. So, to work our way along on this one, if you have multiple colors with you, then what I might suggest is going ahead and putting on your basic tan curve. Tan curve is still relatively new to us, so we're going to build it up in process. So maybe we start off and we say, I know my tan curve starts in the middle and rises. Does that wavy thing. I know that we hit our vertical asymptote at pi by 2. You do not have to label that. In fact, don't label that asymptote. It's not required because you're on a grid. Your reader can see the location of that asymptote based on the scale of each axis. You then know that you get your next 0 at pi as you're doing the wavy thing, and we then hit our next asymptote at 3 pi by 2. We get back to a 0 at 2 pi, and you should be good with then the wavy things occurring. What we have to make sure we are focused in on is also our pi by 4s. So the fact that we know our wavy thing passes through pi by 4, 1. And on either side of the 0, we would have a pi by 4 and 1. We need to make sure then that our curve passes through all of those points. And if we were to draw on that wavy thing, getting closer and closer to each asymptote, and passing through those points, then we produce a really good shaped tan curve. So there is our basic tan graph, and now we need to do all those transformations to it. So what I'd like everybody to do, pause the video, jump in, create a graph for that transformed tan curve. Okay, we're back. So as we take a peek at that, I'm going to take my first 0 and I'm going to perform all the transformations to it. So that value right at the origin. Well, I need to reflect that in the x-axis, vertically stretch it by a factor of 2. Both of those have no effect. I need to shift it to the right pi by 3 and up 1. So if I go to the right pi by 3, given my scale, that's 2 grid lines. So to the right pi by 3 and up 1 unit. Be very careful. Remember, be careful of counting squares. Instead, we got to make sure that we move units. Well, now, the next thing that I'm going to do is I'm going to transform my asymptote. Okay, my asymptote occurs at pi by 2. If I reflect a vertical line on my x-axis or vertically stretch that vertical line in my x-axis, well, then it's not going to seem to have any effect. The only thing that will affect it is moving it right pi by 3, because up 1, you won't see a change either. So there is the location of my new asymptote. I can take my next 0, do the same thing. The reflection, the stretch, no effect. Shift it to the right pi by 3, up 1. I can now do the same thing with my last asymptote. All of those transformations have no effect, with the exception of shifting it to the right pi by 3. Now, what I may do is just do a quick check right then. I know that the normal tan, or period of my tan graph is pi units. And so if I take a look then, since this has not been stretched horizontally, then my final graph should have a period of pi units. And I can get a little confirmation on that my zeros are pi units apart, my asymptotes are pi units apart. Okay, here's where your 1s and negative 1s come into play. So now we're going to do all those same transformations, but to our 1s and negative 1s. Okay, let's take this first one that occurs at pi by 4, 1. I'm going to take that red point and now I'm going to transform it. So I need to reflect it across the x-axis, vertically stretch it by a factor of 2, shift it to the right pi by 3, and shift it up 1. There is the finishing position of that first 1. My red point gets transformed to that blue finishing position. Okay, I'm just going to get rid of all those little blue marks. I'm going to clean up my curve a little bit. And there we go. I have this one little blue mark that's fitting in right down at the bottom. I'm going to try to get rid of that. And there we go. Now, let's take the -1 and let's transform that. Okay, so I'm coming over to this -1, and I'm doing that transformation. Sorry, I also noticed that I erased. Okay, now I have to reflect that in the x-axis, vertically stretch it by a factor of 2, shift it to the right pi by 3, and shift it up 1. There is my finishing position. Now, here's where I'm going to say, if we've gotten really good at doing our tan curves, and we feel really, really comfortable, then we should be able to take the information we've already found, and we should be able to use the fact that your tan curve is periodic to create our final graph. I want you to notice the relationship between the middle of your curve, this X or purple point, and your 1. Because those points have to always be equidistant apart. Because my tan curve, that wavy thing, is symmetrical. So if I was to do a quick count between those 2 points, I notice that I would go pi by 4 down 2. So all my movements then, from the middles, the zeros, to a 1 have to be movements of pi by 4, 2. And you'll notice we just got a little confirmation. Pi by 4. Two. So let's keep using that patterning then to be able to get us through that process. So all I'm going to do then is I'm going to go from my middle of my graph and move pi by 4 and down 2. That gets me the finishing position of my 1s. Now, if I had enough of that to connect, I could create my wavy thing. And so in purple, we're going to then see that I have to be curving up, curving down, and approaching the asymptote. Curving down and approaching the asymptote. Now, what I don't have is then my 1 in the first part of my graph. But if I use that same relationship, then if I went backwards pi by 4, I would have to go up 1, up 2. That would then be the finishing position of a transformed 1 that I could then curve up through that point and be good. Nice. Okay, The only thing that we haven't dealt with, and we have to be careful of, is this last little section. That the instructions have asked me to go through and graph this for 0 to 2 pi, and I don't have any of my purple curve showing in that red interval. It doesn't mean that there has to be. Quite possibly, we wouldn't see any part of the curve in that interval. However, we have to make sure that if one exists, we have it graphed. So, let's take a peek and examine, okay, how are we going to address that red interval? Well, the first thing that I would do if I were you is I'd be conscious of, does my graph show at 2 pi? So what I'm going to do is I'm going to sub in an x value of 2 pi just to see where would the curve exist for that angle value. And so if I just do my substitution, 2 pi minus pi by 3, then I can go through and I can calculate that value. So what I have then is the tan of 5 pi by 3. And if we're still kind of working through our rotation angles, then maybe we're thinking about, well, 5 pi by 3 would be here. That would be a pi by 3, negative root 3, 1 and 2. My tan value then would be opposite over adjacent. And so what we end up getting then is a 2 root 3 plus 1. Now, if we were going through, I'm not saying that you know the value or where to plot 2 root 3 plus 1. So you go through and you get a decimal approximate to that, and you would find out that it was approximately 4.46. So as we do a quick check then, if I was to plot a point on my graph at 2 pi, my curve should be at a point of 4. That would put it like way up here somewhere, up in the problem itself, which tells me that I know that there is no part of that purple graph that should exist in that last pi by 6. So I'm going to get rid of all of that red highlight just so that we don't think that that should have ever been part of our curve. And so if you were to just give me the purple graph on that grid, then you have a great looking tan curve. Okay, we threw a lot of material at you today. The main focus for you, get really, really good at sketching your curves. So, time now, jump in, get some practice, make sure we're solid. Good luck.